Right, in this video I'm going to talk to you about properties of materials and kind of how that has an impact on product design and engineering decisions. Now, every product in our world comes into contact or has to manage certain forces. So let me get my slideshow started and hopefully we can make that fit where I'm working. So you need to understand the forces first of all. So we've got compression. Compression is a squashing force where forces are acting from opposite end. Now it can be in all sorts of directions. It doesn't just have to be vertical. Tension is a pulling force where the forces are acting in opposite directions. We have bending, which is where if you imagine a piece of a plastic ruler being bent on a desk, if you push down in the middle, that's a bending force. Two forces acting upwards, one acting downwards or side to side. Torsion is a twisting force, where something is being rotated. We talk about torque. When we're twisting, torque is the force that we might apply. And then shear is where you have two forces acting in opposite directions. Think about a pair of scissors or two plates that have been welded, that have been bolted together of steel, and then when they're pulled apart, that maybe cuts through the bolt. So that's shear. So if you talk about something being sheared off, so the obvious example, as I say, is a pair of scissors. Now, designers and engineers select their materials and design structures that are able to manage forces acting upon them, because those forces are there and they're going to act on the product. Where the forces are either overwhelmingly large unexpectedly, in the case of earthquakes or impact, that's when you get structural failure. So what designers and engineers would love to do is to mean that nothing ever breaks, nothing ever fails, but the reality is that sometimes there is a compromise between the known forces acting and the availability of materials, or the weight of the final product, or the overall cost, the potential the manufacturing ability in the area, and the availability of the materials. So sometimes you can't have every property absolutely to the max, and you have to make some sort of compromise, and that's where potential failures come from. So you have to be able to understand the forces, and you have to understand the properties of the materials so that you can apply them in the best way possible, and it can be a bit of a juggling act. Okay, so let's go straight into those properties of the materials. Now, it's a bit of a list, and in reality, properties of materials, they often overlap. There's often a bit of similarity between them, or under certain conditions materials exhibit one set of properties, and under a different set of conditions such as heat or moisture they might show a different set of properties. But overall these are our kind of categories, and then you could do some further investigation and testing to talk about specific materials in your own projects. So strength is one of those words that we use all over the place, and it's kind of like, oh, that material is strong, that's really strong, it will last for ages. Strength is actually really important to understand what it is, and it's the ability to withstand the forces of compression, tension, shear and bending without failure. Okay, so there's all sorts of things that can happen to products, but you apply the right material in the right way and you can then describe it as strong. But if you apply that material to the wrong context or the wrong set of forces, then it would not be strong. The examples that I'm giving you, mild steel wire has very high tensile strength. Okay, concrete, on the other hand, if you were to just have concrete, it breaks apart very easily. It has low tensile strength. As a result of that, what we do is we often add steel into concrete to create reinforced concrete. So it has both good compressive strength where it's squashed and good tensile strength if it was pulled. Okay, so that's where you combine the properties of two materials into a composite in that case. Another example we've got here, expanded polystyrene has low compressive strength. You can crush a cup. Concrete has high compressive strength. Okay, so you wouldn't build a building, or you wouldn't build something out of polystyrene and expect it to last if the force acting on it was compressive. However, if you wanted something very lightweight and very good as a thermal insulator, you might employ polystyrene. So you choose the right material and its properties for its application. Okay, remembering those compromises that I've noted there. So if we go into some of these, I think I've got 6 slides here now talking about the properties. Now, Elasticity. If something is elastic, if it demonstrates elastic properties, that means it can stretch, it can change shape, and then return to its original shape. Now, we would all talk about elastic maybe in our clothing or elastic bands. There are classics, or rubber balloons that we can blow up, and then when we let them down, they return to that original form. That's elasticity. Absolutely comfortable with that. But actually, you think about it in other materials and other products, elasticity is really important. We don't live in a super rigid world. Everything isn't very, very stiff and very, very hard. It's actually a little bit stretchy, a little bit bouncy. So if you think about a football, I was doing some research for this, and I was looking for footballs being kicked, and there are some good examples. But I thought, you've got that man's face also demonstrating that it has elastic properties. At the end of that high-speed video that these guys were shooting, his face was in a normal position. The ball had been squashed, his face had been squashed, but then they both exhibited elastic properties and returned to their original shape. Elasticity is also used in things like earthquake-proofing buildings, where the buildings, rather than being built on stiff foundations like you would do in the UK, because we don't really have earthquakes here, places like Japan and New Zealand have to build, in some cases, build on materials that exhibit a little bit of elasticity. They can move and absorb some of those shocks rather than the building being shaken to pieces. I was looking at the weightlifting bars. Now, those bars, if they were very, very stiff, there's a very good chance under the sort of loadings that they're getting, they would snap. So by putting that little piece of elasticity, a little bit of elasticity, by choosing the correct material, they're able to make those bars just have a little bit of spring to them. I believe it gives them a little bit of assistance in lifting it to a certain height. But they're not rigid, although that's not what you might think first of all. They're designed to bend. Plywood chairs, another example of furniture. Actually, if you sit in a plywood chair, it's stiff enough that it holds you up, but it's springy enough that it gives you a little bit of comfort. Okay, so that elasticity is in evidence even in something like a plywood chair. Okay, hard materials are very, very stiff. They don't exhibit any elasticity. Okay. Hardness. Hardness is, again, it's one of those materials, yeah, that's really hard, yeah, that's really hard, it'll make a dent in that object. Hardness is really important to understand. With hardness, the downside of hardness is often brittleness or break, or sort of the ability to snap. We deliberately need hard materials to cut and shape materials that are softer than them. So for example, we can use high carbon steel to cut mild steel, because the carbon content in high carbon steel makes it harder, and as a result we can use a tap, as you can see in the picture there, to cut a thread into a hole in a piece of mild steel. If that tap was made out of mild steel and we were trying to cut a hole in mild steel, it wouldn't work. It would chew up the tap. It would give you a horrible thread. So you have to have those hard materials. We also have hard materials which have really good ability to wear or resist wear. So you could have a shaft that's turning inside a bronze bearing, or the bearings themselves, the balls might be made out of a hard material, and they can last for ages and ages. They don't wear away, and it's the ability to resist wear. Okay, if you were looking around a workshop, the bed of a machine is made out of cast iron. So our lathe beds are made out of cast iron, our drill tables are made out of cast iron, and they're designed so that you can clamp stuff to them, you can slide things around on them. In the case of the lathes, you can move the saddle up and down. You can move the tailstock up and down on it, and it doesn't wear out because it's been deliberately selected as a hard material. It's able to resist wear. The other example that maybe you wouldn't think of in the first instance, ceramic materials such as glass are also very, very hard, but they can be brittle. And the example that I've given you there is a mobile phone. Your mobile phone has got this beautiful glass covering on it, but as everyone knows, they're prone. If you drop them and they get hit in just the wrong spot, they'll shatter, and you'll get a very, 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 very cracked screen. There's very rarely just one crack through the middle of it. And that's because it's such a hard material. If it was a softer material or a tougher material that was maybe a bit more resistant to dropping, the chances are it would also be more likely to get scratched, and so you'd end up with a very foggy screen. Your phone has to be able to go into a pocket with keys and harder materials, or hard materials, and not become scratched. The downside of that, the flip side, remember we're often compromising, is that it's likely to smash if you were to drop it on the floor in just the wrong spot. Okay? It's worth having a look at the diagram at the top. These come from Cambridge University, and they're a study of the properties of materials, and they've kind of categorised materials together. And it's worth reading those two axes. We'll go through those properly another time, but do have a look. I've shown you on the left hand side the Brunel hardness test, where a shaped die is pressed into a material, and the size of the dent that it makes basically tells you how hard or how soft that material is. That's the Brunel hardness test. And then down the bottom we've got the Mohs hardness scale, which is sort of sets out how hard one material is compared to another. A classic test is if you scratch one material with another, whether or not you can leave an indentation or you can leave a scratch mark, and the one that scratches is the harder one. The one that has the scratch in it is the softer one. Okay, so hardness is very specifically able to resist wear. Right, malleability is something malleable. Now, malleability is a really, really important property, and it's there in materials that you might not think of. So we talk about something being as hard as steel. Mild steel is actually quite a malleable material. It's able to be stretched and formed over shapes or under compressive force, under tons of force. And so, for example, the car door there has been stamped out and pressed into a form. Likewise, the stainless steel sink has been pressed into a form. That relies on that material being able to stretch without cracking or splitting. I've deliberately chosen a couple of old-fashioned coins for you. If you think about how they used to strike coins in the old days, it was literally with a die that they'd hit with a hammer, and that material was squashed into position with the I think it's King Alfred probably on that one, in position. So that ability to be pressed into a shape is malleability. But the important thing is it doesn't crack, it doesn't split, and it doesn't tear. That's how you can tell if a material is malleable. Copper is a brilliant example of malleability. There's famous Newlyn copper workers did beautiful work. But if you go right back into history, people were able to beat materials like lead, gold, copper into really, really fine sheet and make these incredibly decorative objects because it is a malleable material. By hitting it and forcing it, you can change the shape of it without it tearing or splitting. I've given you the example there of polystyrene for the vacuum forming machine. Plastics can be malleable, but sometimes by heating a plastic up or a polymer up, you can actually make it more malleable. Particularly thermoforming polymers, such as polystyrene that I've shown you there, if you heat that up under the vacuum former, it becomes like rubber. It becomes incredibly flexible, and it can then take up the shape that you're vacuum forming it over. When it cools, it goes back to being a more stiff object. Again, acrylic is a great example on a line bender. If you heat it up, it becomes very malleable. When it cools, it holds its shape again. If you think about steel, steel is a material where if you heat it to a certain point, it becomes very malleable. When you're working it red hot, it is malleable. The minute it cools, it loses a lot of that malleability. Although obviously I've talked about the sheet material there as well. Right, ductility. Ductility and malleability are kind of, they're connected. So a material that's got a bit of stretch to it is often a tough material. Ductility is specifically something which is able to stretch under tensile forces. So when it's being pulled, it will stretch without snapping. A material with low ductility will snap very quickly. It won't stretch, it's got no give in it, and it will immediately kind of pop and snap. So the example that I've given you on the bottom right is cast iron. That's a good example of a material that is not ductile. Copper is a great example of a ductile material. Aluminium is ductile to a point. I'm showing you the example there with necking in it. Now that's a tensile test. It gets pulled in two different directions and it thins in the middle. Just before it snaps, it will come down to a really thin point, and then it becomes unsustainable and it snaps. Now that's a tensile test, and the result is necking. You can see that there is no necking on the cast iron sample. It's snapped almost in a straight line. Okay, it is not ductile. It can't be stretched. Ductility is important for making things like wire. Lots of metals can be pulled into wires or rolled into wires, but it's the ability to sort of pull it through, and you can do it by hand with things like copper and silver. You can pull it through a tiny little hole and pull it with some draw tongs and actually reduce the diameter but increase the length at the same time as that volume of material is changed into a different shape. Okay, so that's ductility. Something is ductile. Copper is a great example of that. Toughness. Now toughness, a bit like being strong, is one of those words we use all the time. Toughness is actually the ability to take a knock without fracturing. Mild steel is a really tough material. Okay, I know I keep going on about it in this, but it's a really good example of a tough material. Polycarbonate is another really tough material. These are materials that are used where they're often going to come into contact with some quite challenging forces. I'll give you an example of the wheel, or conditions rather. The wheelbarrow is used in all sorts of different ways, often incorrectly, and we throw things into it and we hit things and we mix stuff up in them. People sit in them. There's all sorts of ways that wheelbarrows get used, but because it's able to resist the knocks and generally stay in the same shape and still be usable, you could describe that as a tough material. Likewise, the body of a car is designed to protect the occupant, so it has to be quite sort of strong, durable, but it has to have that toughness so that you can have a prang in a car without it collapsing and smashing into hundreds of pieces. It has to be able to resist that knock. Doesn't mean that it doesn't change shape at all, but it does mean that it doesn't fracture and fall apart. Likewise, if you think about things like nuts and bolts have to be turned with spanners. They're often hit with things. They've got compressive force like mole grips squashing them. That's important that we understand that they're able to withstand those sorts of knocks. And impact drivers and stuff like that, drive screws, and they have to be tough to be able to resist those forces. Polycarbonate is a great example of a tough polymer. Doesn't smash easily. It's used for things like riot shields. It's used for guards on machines. Polycarbonate can be heat treated. It's got really good optical qualities, optical properties. It's almost like glass, but it's really, really tough. It can resist things flying out at your eyes, and it will protect your face. Okay, so I call that shock loading here. Dynamic force is something being thrown at it. Polycarbonate is capable of dealing with that. Again, mild steel is a good example. Toughness. Fuseability. Fuseability, perfect example of fusibility is welding. That's been around for donkey's years. Basically, you get your mild steel, you get your steel, you heat it up to a point where it becomes a liquid, and you join another piece to it in its liquid state, and then when it cools, those two materials are indistinguishable from each other. Now, because a certain amount is lost along the way, or the shape's changed, a filler material is added in usually, so that well, always really, in MIG welding, that's automatically fed into the weld pool, and so you get that fused material, which should mean that if you were to X-ray it, there's no difference between the material on either side of the weld joint if it's been done properly. Same thing happens, you can do with polymers as well. You can do it with flames, you can do it with hot air. It's not so often done because polymers are so easy to form by injection molding and vacuum forming. We don't tend to fuse them as much, but certainly if you think about UPVC windows, the window frames, you can look at the joints in the corners. Those have been fused to give you a perfect joint where, again, the two bits of UPVC are joined, and you wouldn't be able to tell the difference between one and the other. Visually you can. I'm looking at windows, by the way, I'm looking there. Soldering's not exactly there, but if you think about it, what that does is it heats up and it combines with the material by sort of enrobing it. It's not actually the same as two materials coming together and cooling as one material. So it's similar with brazing, although brazing is similar to welding. Fusiability, I'm not entirely sure it covers it. I do think it's important that you think about 3D printing. 3D printing uses fusiability as its main manufacturing process. It's an additive manufacturing process. Material is being put down. It goes layer by layer. Now, if the materials weren't able to fuse, each layer would separate, and indeed, if the temperatures aren't controlled properly, they do come apart. They call it delaminating. So the fusibility of the material, of the polymer, ABS or polylactic acid, is dependent on the temperature being correct and the feed rate being correct. It's worth having a look at some 3D printing to see how each layer is deposited down and it fuses with the layer below it and eventually with the layer above it. Fusibility. Right, absorbency. This is a bit of a complicated slide because there's actually two sorts in here. in most cases, we're going to talk about absorbency of liquids in this case as a property. And then on the other side, the right-hand side of the slide, I'm talking about absorbency of light. Let's just talk about the liquid for a minute. Classic example would be a baby's nappy absorbing water, or a bath towel. They're kind of obvious examples where water is taken away or moisture is taken away from where we don't want it and trapped and held in some sort of system. The silica gel you get with the little packets, that you might have always wondered what that is. That's designed to absorb any ambient moisture whilst products are being stored and delivered. Silica gel, that absorbs moisture as well and holds it in place. Sportswear, sports equipment, we talk about wicking and where the sweat is removed from the body and it's put out onto the surface of the material to evaporate. A certain amount of that is held whilst it's evaporating from the top. So that absorbency, that taking away of liquid is really important. Now, if you have materials that are absorbent but they're not protected, they can quite often rot. Examples are things like if you were to build a shed in your back garden and you didn't treat it, then that could rot as the moisture and the rain got into it. So we often put a coating of paint or something or a sealant into it to prevent it from rotting. Okay, so absorbency is really important. I think you kind of it's quite an obvious one really. Think about a sponge or a flannel or whatever. It absorbs liquid and you can do what you want. You can manage the liquid then. Absorbency of light is a slightly different case, but it kind of falls into the same category. So I'll put it on one slide. Generally speaking, we talk about absorbency of light as being important for from a design and technology and from an engineering point of view. Probably your solar powered cells, your light sensitive cells that generate electricity or heat water. They absorb the sun's rays and they generate heat or they generate electricity. The other way to think about absorbency of light is how some light is reflected, and depending on which band of light is absorbed and which band of light is reflected, you will get different colours of objects. When you look at something, it depends on which band of light is being absorbed and which is being reflected as to how it appears. Now, a material that absorbs all the bands of light sort of becomes invisible. It becomes a very dark shape and you get no profiles. And you see more examples of that these days on vehicles where the profile is disappearing. You see examples of that on sort of props and things like that people are designing these super absorbent paints or coatings so that objects can sort of disappear in some respects. So, but for me, absorbency of moisture is probably the most important one from a design and technology and engineering point of view. But don't forget, you can also absorb you can also absorb light. Right, electrical conductivity and thermal conductivity. Again, these two are different, but they often exist in the same products, which is why I've got them on the same slide. You have a conductor and you have an insulator. They're the two opposites, conductive and insulator. Electrical conductivity is where the electrons are able to pass through the material. Thermal conductivity is how heat is able to pass because the molecules sort of vibrate and transfer that heat energy. So usually the same materials. So I'm going to give you a couple of examples. If we're dealing with electricity and electronics, gold is beautiful it's a gorgeous material, but it's a really good conductor of electricity. But because it's so valued, it's really, really expensive. So consequently, we can't use gold as our main material for electricity conductivity. We use one of our others. Now again, silver's a really good one. But we go down to copper. Copper's relatively abundant. We can get hold of lots of it. It's reasonably cheap. It's a malleable material, which means that it can be formed how we want it. It's a ductile material, so we can draw it into wires. And it's a good conductor of electricity. So because of all of those things lead us to copper being a really, really good conductor and being used in lots of situations. However, where it needs a little bit of stiffness, we quite often find brass or bronze being the replacement for copper because, again, cost. So if you think about a plug has brass prongs sticking out of it. If they were to be copper prongs, they'd bend and the plug would soon become useless. So the properties of those materials have to be balanced. Electrical conductivity versus stiffness and hardness. And in the case of a plug, the prongs are as a result, brass. Thermal conductivity. Quite often you get a pan which is copper bottomed, or we get aluminium pans which allow the heat to conduct through the entire body of the material, which means that you get even cooking. If you think about, I've given you some examples of cups there, all of those are designed to hold heat. They all conduct heat to a certain degree, but I think you'd agree, if you've ever tried it whilst you're out camping, if you try and drink a hot drink out of a tin mug or a metal mug, you stand a really good chance of burning your mouth. Whereas if you drink it out of a ceramic mug, you're less likely to get a burn, because some of that heat isn't conducted as well. Okay, so conducting heat is really important. Insulating probably is as important with heat as conducting it. So the way we insulate our handles on our saucepans is to make them out of wood or to make them out of polymers, which are less conductive. The way we insulate our houses is to put foam and materials in that prevent the heat from being able to pass through. So we use insulation to prevent conduction of heat. Okay, little bit confused there, but I think the idea is that conductivity can be electrical or it can be thermal. You can have a thermal insulator and you can have an electrical insulator. All right. Often we want things to conduct. When we don't want them to conduct, we want to be able to apply the property of insulation. Density. Now, density as a property is a bit of a rare one to talk about, because we might say that something's really heavy, or we might talk about the mass, but actually density is a measure of how heavy an object is for a given size. So if you were to take a cube of polystyrene, which is 100 by 100 by 100, and you were to take a cube of concrete, which is 100 by 100 by 100, and you were to take a cube of cast iron, 100 by 100 by 100, the cast iron would weigh significantly more than the polystyrene, although the object is the same size. And that's density. Now, gold bars are a classic for density. You see people on movies with gold bars, and they lift one up, they can hardly lift it, it's so heavy. Gold is a really dense material, but remember, density is not the same as hardness, because gold is also malleable, isn't it, and ductile. So density is the weight of an object, the denseness. Things like cast iron are really important for things like weights. If you want a given weight to stabilise an object, or if you're weight training, you want to know how many kilograms you've got. Cast iron is a fixed density. You know what you're getting. You can make it exactly the right size to give you the weight that you want, the load that you want. Likewise with cranes. Cranes are very, very thin structures. They're often, particularly these tower cranes like I've shown you in this picture. It's a brilliant engineering piece where all of those loads are very, very carefully calculated, and the structure of the crane is triangulated to transfer those loads. But they wouldn't be able to lift the heavy loads at the end of the arm without having these concrete blocks at the other end, which act as the counterweight. They're the balance, and without having the counterweight, the crane would collapse. That counterweight can be moved backwards and forwards according to what's being lifted, and other weights can be added so that the crane can do its job. Okay, but you wouldn't be lifting up great big blocks of polystyrene, great big blocks of wood. Concrete is a really dense, heavy material, and therefore it's an effective counterweight. Giving you the example below of a flywheel, which is obviously part of an old steam engine. I was trying to find an example that kind of showed you the principles. So flywheels are still in action in vehicles now. They're much smaller than the example that you can see there. But actually what a flywheel does is it stores kinetic energy, and it makes it available on its next cycle. So as it rotates around, once you've got a flywheel moving, it can run and run and run with just a small amount of input power. Okay, an example might be if you're pushing someone on a swing, every now and again you need to push them again, but it's nothing like the force that you need to get them going in the first place. And that's how a flywheel acts. Now, flywheels only work if they're made of a heavy material. So again, if we had a wooden flywheel, it would soon stop spinning. It wouldn't have the density and the weights to keep that kinetic energy going. It would lose its momentum. Okay, so something like cast iron, because it's a dense material, is able to continue to spin long after a less dense material. Now, like I say, don't think it's only in the case of old steam engine stuff. Flywheels are very much part of our efficient green energy generation, because they're used to keep motors going once a small starting force has been applied, or a larger starting force has been applied. Right, then on to another use of dense materials, which is for shielding, radiation shielding. I thought it was worth putting this in here. If you've ever been to the dentist and you're having an X-ray, you'll notice that the staff will often step out of the room, or they'll put on an apron or an overcoat, which is different to their normal garb, and that's usually where it's got a thin layer of lead inside it to prevent any of those X-rays from penetrating and causing damage from overexposure to radiation. So density, it's an interesting one. How heavy an object is for a given size. And think about that cube analogy of a polystyrene cube and a cast iron cube. Right, so I've given you some examples here to have a look at. If you're doing BTEC or engineering or GCSE, at some point you're going to need to talk about properties of materials either in your product or if you're disassembling other products. You would talk about why the person who's come up with that product has chosen those materials. You only get the good marks if you justify. You only get the good marks if you explain. If you're only labelling, so for example you might say these are washers and they've been given a zinc coating. But if you don't then go on and talk about why they've been given a zinc coating, or why they're able to withstand a compressive force, or why they could be stamped out without breaking, then you're not going to get the top marks. So in those examples, I'm not going to read through them all. I've kind of underlined where I'm seeing properties as being an important feature. So have a look at those examples. And then finally, I've given you some examples of how you might be asked to answer a question in a GCSE. I've been quite focused on specific products. Actually, products are often made up of 2 or 3 materials. So if you look at a 9-mark question for each one of those would be 9 marks rather than all 4 for 9 marks. You're going to be looking at 3 properties where possible. You may be looking at 3 components, and you're going to be looking at weighing up maybe the pros and cons. So if you remember, I was talking earlier about copper as an electrical conductor. We can now look at that plug and we can talk about the body of it being an insulator. We could talk about that body being able to be heated up in its manufacturing stage, and it becomes malleable to be able to form it into the plug shape. We can talk about the brass pins that are brass because if it was made out of copper they would bend, they'd become deformed, but brass is also a good conductor of electricity. You might talk about the black tape being an insulator, or the black coating around 2 of those pins being an insulator, which is therefore able to help prevent electric shock if people are pulling it out without taking a lot of care. I've deliberately given you the example of a 3D printed phone tripod. Make that clear, that is 3D printed, it's not injection moulded. And really, if you're discussing this one, you ought to be talking about the tripod rather than about the camera or the mobile phone. But if you ran out of things to say and if you think you've only made a couple of points, then maybe you start talking about the camera and you start talking about screens and lenses. Ball peen hammer, you'll see that there's 2 different materials there. Think about how that's used and think about the ergonomic comfort for the user, but also think about the function that hammer has to perform. And then the Play-Doh barber set, I deliberately chose that to allow you to discuss at least one of the properties that we've taught there. You've got the material that the Play-Doh itself, but you've also got the material that the Play-Doh system is made from, and I thought, my eye is drawn straight away to the handle, which is going to have to resist certain loads as it's turned to be able to force the Play-Doh through. So there's something for you to have a bit of a think about. So as I say, each one of those should be 9 marks. I'm not giving you 9 marks for doing all 4. That is a 9-mark question. In the exam paper, you would normally be given 1 product. So in effect, you've got 36 marks for that. Okay, so properties of material. Remember, it's often a bit of a compromise. You need to use the correct terminology in your exam papers and in your assignments so that you're able to get the top marks for justifying and for explaining. Don't just describe. If you can use the correct terminology, give reasons why, weigh up the pros and cons. All right, good luck with that.